What we're going to do is the following calculation. Calculate the wavelength in nanometers of the spectral line produced in the hydrogen spectrum when an electron falls from the 8th orbit to the 4th. What we have is we have an electron that is on the 8th orbit, which is n is equal to 8, and we are going to look at the wavelength that is produced when the electron falls to n is equal to 4. The energy that's released is released in the form of light, and we can determine the wavelength of that light by first determining the amount of energy that's associated with it. There are 3 steps to doing this calculation. The first step is to use Bohr's equation in order to determine the energy of the electron at the 8th level and the energy of the electron when it's on the 4th energy level. The formula that we use for this is Bohr's formula, which is minus B divided by n squared. B is a constant, and the value is 2.18 times 10 to the negative 18 joules. And n is the energy level of the electron. So when we're on the 8th orbit, the value is 8, so then it's going to be divided by 8 squared. When we put this into our calculator, we find that we have the value negative 3.406 times 10 to the negative 20. And the unit is joules. When we do the same work for E4, we've got negative B, which is 2.18 times 10 to the negative 18, divided by 4 squared, and we'll have the value 1.36 times 10 to the negative 19 joules. So you're going to want to make sure at this stage that you know how to use your calculator properly with the scientific notation so that you can get these values. The next thing that we need to do is find the difference in energy. And to find the difference in energy, we're going to take the energy of the electron when it's at the higher level. So in our notes, we say that that's EH, so E higher, minus the energy of the electron when it's at the lower level. So when it's at the higher level, it has a value of negative 3.046 times 10 to the negative 20, and we're going to subtract negative 1.36 times 10 to the negative 19. Now you should get a positive value for this if you entered the negatives into your calculator properly, and we get 1.02 times 10 to the negative 19 joules. Now that we know the actual amount of energy that's being released, we can convert that into a wavelength. And we have a formula which is E is equal to hc divided by lambda, where lambda is the wavelength. And when we rearrange this formula, we have hc over E. So you want to be comfortable with that rearrangement. Now H and C are both constants. I'm just going to use this space over here. So H is Planck's constant, and it has a value of 6.626 times 10 to the negative 34 joules seconds. C is the speed of light, so it has a value of 3.3 times 10 to the 8 meters per second. And we're dividing by our energy, which is 1.02 times 10 to the negative 19. Because Planck's constant is in joules second, and this is in meters per second, and this is in joules, our final answer that we get, which is 1.945 times 10 to the negative 6, is in meters. Now, in order to read the electromagnetic spectrum, and because the question asks us to, we need to put this into nanometers. To go from meters to nanometers, we need to divide by 1 times 10 to the negative 9. And so we are left with 1,945 nanometers. Now this calculation in particular is difficult in your calculator if you're not using the functions properly, so you want to make sure that you're using the scientific notation properly in your calculator, and if you're having trouble, make sure that you ask. The next part of this question is to identify whether or not the spectral line that's produced is visible to us and to justify our choice. In order to do that, we need to look at the electromagnetic spectrum, and there's only a small range of wavelengths that are visible to us. We're only able to see wavelengths between 400 and 700 nanometers, and so our value, that is 1,945, is going to be higher than what we're able to observe, and in fact it's going to be in the infrared. So when you're justifying your answer here, you can say we are only able to see between 400 and 700, therefore we cannot see it, or you could say this is in the infrared, which is outside of the visible region. Either one of those would work as a justification.